So good afternoon. So what I'm going to talk about today, so the theme of this year is AI, right? So then everybody knows AI nowadays is really talking about deep neural network or deep learning. And what I'm going to talk about is how do we turn this deep neural network, deep learning into some kind of system or product. That's what I'm going to focus on. So although the term AI is pretty ubiquitous and then pretty hot nowadays, really what we are talking about is deep neural network or the machine learning technology enabled by deep neural network. When I was a graduate student, we also studied neural network. But at that time, neural network is shallow, right? It cannot contain more than one or two hidden layers. But now with algorithmic breakthrough, now we can do hundreds of layers of hidden layers, and suddenly it has many applications, and that's what everybody is excited about. So the kind of AI system based on deep neural network could be something like this autonomous driving. Do I have a pointer? The autonomous driving vehicle or drone or robot. But like I say, the deep neural network is really about machine learning technologies. Things like, today, maybe you can have, when you want to write a pattern recognition application, you get a small number of people to define a spec, to come up with an algorithm, to write the code for it, and then eventually you have a software. But in the future, when you do machine learning, what do? You get a bunch of people to label data for you. Once you have this labeled example, we have a machine learning algorithm based on DNN that can extract the knowledge embedded inside this label example and then create finally a DNN model out of it. That process is machine learning. In other words, previously we write program line by line. In the future, we use a universal algorithm to come up with software, which is in the form of some sort of DNN model. And then I just want to give you a general idea of what it is. I mean, for most of you, you probably don't really know what DNN is, but in your next couple of months, people will talk to you about DNN. So you might as well learn what it is, all right? So on the left, basically you have a network, layered network, right? So you have an input layer, and then a bunch of hidden layer, and then you have an output layer. So the input layer could be, I want to recognize an image, whether an image contains a cat, a dog, a pig, or a flower, or anything. The input layer you place there. And at the output layer will tell you that out of this 10 category, does it contain cat, does it contain dog, and so on, right? And the idea of DNN is to train a DNN model like that, in that particular layered model, in order to recognize something, like what I just said, right? And then there are basically two things. One is called a training phase. On the top, basically says that you give me a large number of examples. In each example, you tell me this example image contains a pig. This example image contains a dog. This example image contains a flower of some kind, and so on. And then going through a training process, then I can create a DNN model that can capture that knowledge embedded in the label examples. Okay. Then me. So in this training process, we basically give a, okay, let's try again. In this example, we give a first training image, and then we tell you it's a cat. Second training image, tell you it's a dog, and so on. Once you give this input-output pair, enough of them, let's say 1 million of them, then I have a training algorithm. I can calculate all the numbers, weight on these limbs of the DNN model. Once I get that done, then I have a DNN model. That's the model that can recognize image, whether an image contains a cat or a pig, and so on. Right? And that's the training phase. Once I have a model, I can apply it to your actual application. Let's say you embed this DNN model inside an autonomous driving car or inside a smartphone, and so on. That process is called inference. Then in that case, you use camera to capture some real-world image and apply it to the input layer. And this already trained DNN model can tell you whether it contains a cat or a pig, and so on. That process is called inference. And so remember, there's a training and then there's an inference. So once we know how this DNN actually works, then we ask ourselves, people in this audience who are interested in some kind of IT hardware and software system, they can either speed up or do something about this DNN training and inference. So here we mainly focus on training. Look, like I say, the DNN model training can be the future programming. Right? The programming, you don't need to write program line by line anymore. You just give me a nonce example, then I'll tell you. I will extract the knowledge embedded in those labeled example. So in the process of training, we worry about two metrics. One is quality, like the accuracy of the DNN model. The other is speed. How long does it take to train a DNN model? If you give me 1 million example, how long does it take to give me to result in this particular DNN model? So we mainly focus on here, but in real world, people worry about both quality and speed. For quality, in a nutshell, what you really need is high quality label training data. You need to have that. And to collect high quality label training data is very expensive. So if you have some technology that can speed up the collection and labeling of this high quality training data, that's a win. That's something we can help the community. Or you can speed up the training speed. Like others need to train 3 weeks. You say, use my system, you only need 3 days. Then it makes a big difference, obviously, right? So how do you do that? Now, in my mind, there are actually 2 things you need to do. When you actually do DNN training, usually you have to go through a number of rounds. You have to give me this is training example, 1 million image. I have to set some high level parameter and train it. And then I get my DNN model accuracy is 68%. Not good. So I retune my system, high level system model, train again, and then you give me probably 71%, and so on, right? So if you want to reduce the end-to-end training time, you need to reduce the total number of rounds required. And for each round, you need to reduce the computation time associated with each round. That's how you get the end-to-end training time to as small as possible. That's how you do it. And then the other aspect of it is inference. Like I said, there's a training phase and there's an inference phase. Here, that people are talking about how do you build some sort of specialized processor, maybe associated with smartphone or autonomous driving vehicles, so that once you are given a DNN model, how can you compute that DNN computation in real time and in using as low power as possible. And the third item is really explainability of this layered DNN model. The problem here is that although DNN model actually work, but in practice we don't really know why they work. We more or less know that the whole thing empirically can work as what we want it to work. But to actually explain how the underlying dynamics of a DNN model so far remains a mystery, at least to the research community. And why is that? It's not just an academic exercise. If we don't understand something, how can we use it? The sad fact is we are using it, right? But for certain application, that's not something that they can use. For example, if I'm using a DNN model to do maybe breast cancer diagnosis, the doctor needs to know why. You cannot say the model says so, right? You have to say the model is checking out this very symptom. That's why it concludes that you have breast cancer, for example. So to be able to explain the dynamics of a learned DNN model still is important for practical application. So what I'm going to talk about mainly is about this part. Like for a single run, how do you reduce the computation time? So NVIDIA has a very popular product called DGX-1. This is now at least very popular in Taiwan. You have to wait in line to get it, right? And then a lot of the researchers, they're not just in academia, in like big company like TSMC, for example, they are waiting in line to buy this kind of device. And this is an appliance to speed up DNN training. So it has 2 versions. One version comes with a P100 graphic card, and it charges you about 130K USD dollars, and the other is V100, it's about 150K. So it's relatively expensive. So each appliance has 8 such GPU, either P100 or V100. And then of course the x86 server with 8 such GPU and with everything. And so that's its spec. And here the right hand side is the system architecture, how these GPU are connected. So the claim of fame of NVIDIA has this technology called NVLink. They can link all these GPU together, right, pairwise. Like this guy can connect to this guy, this guy, this guy, and this guy. Right? So it's almost like a fully connected mesh among these 8 GPU. So that's not something that you can do. You have to go along with it. Only NVIDIA's appliance has this. And this appliance also comes with a full software stack for you to do that. So it's not just hardware, it's a full software stack. You open up the box of the DGX appliance, then if you are familiar with TensorFlow or Caffe, you can immediately use it. Right? And then the statistics show that if you use a generic, maybe 20 x86 server cluster, it probably takes you like 3 weeks to train something. Here, it only really takes you probably like a couple of days, like 2 to 3 days. Then the same thing would actually happen. This has been demonstrated in multiple sort of application already. So in terms of the performance, it's really great. Remember, an entire DNN training takes multiple rounds. So if a single round takes you 3 weeks, it's not going to fly, right? You're not going to go very far doing whatever research or whatever development you are working on. So what we are trying to do is saying, still, that thing is very expensive, right? It's like, in Taiwan dollars, it's about like 5 million Taiwan dollars per piece. It's like beyond reach for most of the company, right? Beyond reach for most of the university and so on. So what we are interested in is there any way we can reduce that cost and then provide comparable performance? And that's the goal, right? We are trying to do about this. And how do we do that? Then we try to analyze the cost component of that DGX appliance. It turns out that if you use P100 or V100, that's the price point we are talking about. It's about $6,000 per piece. Per card, it's about $6,000 US to get the card. But NVIDIA also has other kind of GPU, like those that are used in gaming PC, right? One of the most famous one is 1080 Ti. That costs you about $700. So right there is in the order of magnitude reduction, right? So you don't have to do anything. If you can replace the GPU card in a DGX with this, right there, it's going to a significant drop. Now, the only question is that, can this actually compete with the P100 and V100 in terms of performance? The answer is yes. So for 32-bit performance, 1080 Ti is actually better than P100 and T100. P100 and V100 are good because they are very good at the 64-bit arithmetic. But for most of the DNN training, we don't need that. We don't need 64-bit. This is also proven that you don't really need 64-bit. 32-bit is just fine. Right? So if we can build a appliance using this component, that would be a big win. Then of course, the only problem is that all these cards are not designed for server-grade application. Their thermal management capabilities are not really up to par and so on. So that's something we are interested in exploring. And of course, why restrict ourselves to NVIDIA? We can use AMD component as well, or even Intel's 9mm, or even using FPGA. So these are the things that we are exploring as well. So in other words, we are trying to build an ecosystem. Imagine that if everybody agreed that DNN training is important, then DNN training appliance of some kind would be an important system that a lot of people might want. And then we are trying to build an ecosystem that can use interchangeable hardware. But the upper layer, higher level software stack remains the same. And then of course, like most of these DGX only have 8. Now, if our appliance can use 16 of this lower cost GPU, then probably it's also going to beat this higher end appliance using expensive GPU but smaller number of them. And also system interconnect. How do we interconnect all this GPU? Like I said, that DGX has this NVLink technology, and we are trying to push PCIe network. Right? We don't really need anything special, really. NVLink is a specialized PCIe technology. We could have just bumped up the underlying PCIe network. Like, it's not just a single switch, it's a mesh network, just like your Ethernet network. And we can use PCIe switch just like an Ethernet switch. Then we can increase their cross-section bandwidth among the GPU. Then that could also be a win. And finally, of course, one of the issues that we need to address is cooling issue. That, always all these things, how do you cool them efficiently? And then that's the hardware part. In the software part, of course, we will stick to the standard. Like right now, DGX mainly focus on CUDA. CUDA is a proprietary standard of NVIDIA. And everybody else is going for OpenCL. So we are going to go for CUDA and OpenCL. And then what users are interacting with are so-called DNN training frameworks. These are the terms that you run into in your career, like Caffe, NV Caffe, Caffe 2, or TensorFlow. These are all very common DNN training network that normal users use, right? So we have to pour this DNN training framework on top of our appliance. And then there will be a bunch of ideas to improve their performance that we are working on. In addition, we have these 2 more components. One is called DNN Integrated Development Environment. Like I say, to reduce the end-to-end training time, what do you need to do? Reduce the total number of rounds, and then reduce the amount of time per round. Now, reduce the total number of rounds, you need some way to guide the user how to set this high-level parameter, right? And that's what we call DNN Integrated Development Environment. I'm going to elaborate this in a moment. And the other component is called DNN model compression. Once you have DNN model, you already train it. The accuracy, 98%, pretty good. But once you just have this DNN model, usually the DNN model has a lot of redundancy. And we want to convert it to smartphone or vehicle, it's too big because your embedded system doesn't have enough memory to hold it. So you need to compress it. And that's another component that we'll build into our appliance. So not only I'm going to give you a high accuracy DNN model, I'm going to give you a usable one that can fit into your budget on your endpoint devices. So like I said, this is the IDE idea. So I give you the analogy between DNN training and software programming. Today when we do software programming, we use an IDE, right? They give you how to edit the program, compile, debug, and so on. Now DNN model training should have the same environment. So for example, just like when we write program, we don't start with the blank sheet or paper. We start with some library that people already have as a template. So when we do DNN training, we also want to start with some existing DNN model as a base, and then we grow on that, right? So that's the notion of transfer learning. Like you have to know, okay, now I'm going to recognize gunshot. For example, I want to develop an application that can recognize gunshot. Turns out this is a very important application for security. Like in the airport security, they need this kind of application. Then what's the basis I should use to grow this DNN model? So that's transfer learning. And the other is what I say, this is a hyperparameter, high-level parameter you need to set. Either we can automate the tuning or we can provide guided tuning so that users doesn't have to spend a lot of time tuning this high-level parameter fruitlessly. They don't wander around and then set the wrong term and then wasted a lot of time. And finally, the debugging. Like once the most frustrating part of a DNN trainer is that I get this DNN model is 78% this round, and the next round 79%, the third round back to 77%. So I'm back and forth doing this and that, and I don't know what to do. So if we are writing the actual program, I have a debugger. I can single step through my program and say, okay, there's a logic here, that's wrong. That's why your program doesn't do well. But for DNN training, I don't have that. I need something that can provide more informative idea of why my current DNN model is not doing what it is supposed to do. And that's the notion of debugging. So what's the notion of debugging in DNN training? That's something that we are exploring and then have some useful idea already come out already. So that I think is also very valuable for whoever wants to develop and market a DNN training appliance. So like I said, we have this thing that we have an editor for you to edit your neural network, and then you can start with some existing model to do it, like transfer learning. And then this meta learning is helping you to set that hyperparameter automatically or in a guided fashion. And finally, there's a debugger. Like when you have a DNN model, I can clearly see that, okay, you are overfit, you are underfit, and then right now you should set this hyperparameter, grow it a little bit bigger, and by how much, and so on. So that's the kind of thing that DNN IDE is supposed to do. Okay? So that's the first part. Basically, I'm saying that we agree that DNN training should be a very important part of our future. That it's going to be an important element of building future software. So you need some kind of system that can help people to do DNN training. The second thing is that if you want to grow, so you have to build a DNN training appliance, and you want 100 of them. So they can provide the DNN training as a service. Then you need something called hardware as a service technology, HaaS. So basically, what we are trying to say here is that we are pretty familiar with AWS. So they allow you to lease virtual machine. But what if you want to lease hardware, physical machine? And HaaS is allowing you to lease of this physical machine. So you can go to some place and say, I want to get a physical data center instance, not virtual, physical data center instance. Then this particular service provider will give you a PDCI for that. And the most important challenge is that users, once he gets a physical data center instance, he can only remotely configure, monitor, and install OS and application and server in this PDCI. That's the most challenging part. Like today, if I have a bunch of machines here, and I have to configure it, do bare metal provisioning, it's not a problem. Once I get stuck somewhere, I can go in and then take a look at it, what happens. But if I turn it into a service, most of my users are accessing this through a network, remotely. So how can I enable them to do the same management as I'm able to do it when I'm physically close to these machines? So that's the challenge of HaaS. And why do people want HaaS? Our conjecture is that for many applications, they don't really need virtualization. They don't want to pay the overhead of virtualization, like big data or DNN training or high performance computing like DNN sequencing or whatever. Just raw computing power is not enough for me. So why would I want to do virtualization? Okay, that's one. And the other is, of course, that you have this new virtualization technology called container. So it's a lightweight virtualization technology. That means that I don't want to do this like a heavyweight virtualization. So just give me a bare bone hardware and I just run my container management and that's good enough for me. So I give you this comparison. Like in a traditional ISU, that's where AWS is. Basically, you rent a virtual machine, and this IT hardware is owned by the service provider like Amazon, and the hardware management is done by the service provider. And in the case of HaaS, the basic unit of rental is a physical machine. The IT ownership is still a service provider, but the hardware management is managed by the user. And then there's a co-location. That's a more traditional model where the service provider basically rent the rack space. He give you rack, all right? And the IT ownership is the user. User have to bring in the hardware. And of course, user have to do the management and so on. And so that's somewhere in between. There's this model of the service provider own the hardware and then give this complete control to the user. Now the technical building block for this E3 HaaS is that you have two things, like deployment time and runtime, right? So like if somebody call in and say, I want 20 physical machines and they should be connected in this way and I need this much storage, do it. And somebody has to provision it and then give it to it, right? So you need to do server provisioning, you need to do storage provisioning, you need to do network provisioning. So they can give the user a PDCI, a physical data center instance. And the most challenging part is really network, right? Like you and I each get a PDCI, but we share the same network. What is the guarantee that your stuff will not interfere with my stuff, right? After all, I'm supposed to get a physical data center. I don't want to be mingle with you. I don't know how, how clean you are, because you probably have a lot of virus, and I don't. But I don't want to live in the same apartment with you, kind of mentality, right? So you need to do a lot of work in the network provision. Now, once you get PDCI, then at the runtime, somebody has to manage it. Right? I already rent 20 machines and network. I need to monitor it and manage it and so on. So HaaS provider need to do this, and HaaS tenant also need to do that. HaaS tenant is the guy who rent this PDCI. So in the server part, we have this technology called BAMPI. That's something that we have been developing over the years. So the basic idea is a bare metal provisioning for servers. So that's a problem that a lot of people can relate to. So the basic idea is that we have a bunch of machines, and I need to be able to set up the BIOS option, EMC option, hardware option, OS option, and so on. And this traditionally is done manually. And there's a lot of errors, right? That people make mistakes, and then once people make mistake, you don't know which machine is a mistake, so you roll back. Everybody, do it again, and so on. So with this kind of software, you can reduce error, you can lower cost, you can speed the deployment. Okay? And the challenge is, of course, there's nothing on the hardware, nothing. There's nothing on the hardware, and you are supposed to do all this bare metal configuration correctly and in a reliable fashion. So our idea is that the only thing a hardware vendor needs to do is set the MAC address right. Everything else is automated. So you don't have to worry about BMC option. You don't have to worry about BIOS option. You don't have to worry about NICA or RACA option. Everything is automated. Okay? And then you can scale up to hundreds or thousands of machines across different subnets. If you sit on all these subnets, it's not a problem. You can do it. So that's the view, right? Basically, user have a server list. You have a set of server you want to do. That's a BIOS or BMC configuration. That's an OS configuration. And you have the kind of first OS image you want to install. So it could be a Linux, Windows, or VMware, or whatever that you want. And then we can set it up on this bare bone hardware without any additional software running on this. That's why it's called bare metal, right? Nothing on the hardware, and then you can do that. So one of the nice things I think is that we have this robust error handling. I think that's the most valuable, right? When you set up 100 machine and on the 76 machine something happens, you know exactly what happened. Like previously you do it manually, you have no choice but roll back everything because you forget. Right? Maybe I make a mistake in 71, maybe I make a mistake in 79, and so on. With this, we have complete login, so we can do the proper recovery and so on. So that I think is very powerful. And this usually just used when you start a data center, you need to go through this process once. With HAAS, every time a new customer acquires a physical data center instance, you need to do this. So it's every time you get a PCDI, you need to go through such a process. And the other aspect of this HAAS is network provisioning. So like I say, you need to isolate. So I have a single network with 100 machines. I ran 20 machines to you, 30 machines to you, 40 machines to you. You each have your own network requirement. And I somehow have to isolate tenant A's network from tenant B's network from tenant C's network in a way that we can prove to them that nobody can interfere with anybody else. Okay, that's what we are trying to do. So what we are doing is that there's also some nitty-gritty detail, like just to be able to discover the physical network connectivity is a problem, right? So like I have all these machines connected. I don't really know machine number 39, which is port of which switch is connected to machine number 39. And what is the IP address, MAC address, and so on. Just those details. It's pretty annoying if you don't have a good tool. And then of course you need to do network isolation, like what I say. And then you need to, once everything is up and running, you need to do this tenant-aware network traffic analysis. So I'm going to go over some of this important idea for you. So the first problem is what I just said. I have 1,000 machines. I just need to know a particular IP address assigned to a machine. And that machine with a particular IP address somehow seems to be malfunction. And I need to send somebody to the physical data center to see which guy. And then you don't know. Because you only have an IP address. You don't have its physical location, right? So that's a problem. So we have a technology that allows you to do that. Now I can pinpoint a particular server based on which port or which switch that is connected to. Then I can do that for you. Okay. So this is about physical connectivity and physical locationing of individual server. That's one technology that we have. And the other is what I said, tenant-aware network traffic analysis. I'm going to use an example to explain to you why it's powerful. Right? So let's say this is a physical data center. You have a bunch of machines on the left, and then these are all switches. Connect them, right? No problem. This is a physical topology of a set of machines. Then the first question I want to ask is, what is the topology what is the physical network topology that is assigned to tenant A? So now I can give you. Tenant A's virtual network is like this. Okay, so I give you one view of tenant A network. Then I ask, what's tenant B? What's tenant C? What's tenant D? And so on. I can give you that. So not a problem. Okay, so far so good. At least you know that which physical network is now used by which tenant now. Okay. And then something happened. So on my physical network, some link pop up saying that this particular link seems to be overloaded. There's a lot of traffic going on that particular physical link, this link. All right. Now I want to say, who is the guy that actually caused the trouble? Right? I want to know. Right? So then I can tell you that, okay, let's look at that particular link. Then I see that there are two, on that link there are two direction traffic. One is about 800 megabit, the other is about 500 megabit. So I say, this guy might be the problem. Okay? This is this direction. Then I ask, like, which tenants are actually using that particular direction of that particular link? Then I say there are three guys, tenant A, tenant B, tenant C. And among them, tenant A uses this much traffic. So it looks like tenant A might be the troublemaker. Okay? So now I know tenant A. But I want to zoom in further. Tenant A actually has a lot of VLAN associated with it, or IP subnet associated with it. Exactly which VLAN of tenant A that's causing the trouble. So I can drill down further. Then it turns out that tenant A has these 3 VLAN. Then this guy seems to be problematic. Like VLAN 1301 is a problematic one. Right? But I don't have to stop there. I can say, within this VLAN, which host pair is causing me trouble, right? So now I know on that particular VLAN, there are 3 host pairs. They are using the VLAN. Okay? It turns out that this particular host pair, 10.5 and 10.3, these are the culprit, the real troublemaker, the root cause. But then I don't have to stop there. I want to know what is the traffic that these 2 guys are talking about. So that I can say, let's just look in and then see, okay, it turns out that I can use this thing to see that these 2 traffic, there's this particular, there are 3 connection, network connection going on. This connection is a problem. So now I not only zoom down a particular tenant, a particular VLAN, a particular host pair, a particular network connection. Now I say, let me look at it, what exactly is happening there. So from that high level on the network, I see a trouble flagged as a red link. I can go into a particular network connection that seems to be causing the trouble. And this is TCP dump for that particular network connection. Okay, so now that's what we can do. And of course, we can also apply deep packet inspection to further look into that network connection, or it's actually uploading something to Dropbox, for example. Or that's what it's trying to do. Okay, then we can also zoom into this kind of thing. So that's what we mean by a physical data network. And it has tens of tenants there. Some trouble happens. I need to know which tenant is causing the trouble. And I also tell you which host network, which host pair, or which applications are causing the trouble. And that's the beauty of this technology. Like when you want to run a house, that's indispensable. You cannot get away with it. Like you can provision this, you can provision that. But once it's running, you're going to run into trouble. And then this tool can help you resolve the issue pretty quickly. And of course, there are other components that can give you this more mundane thing about prepare hardware, make sure all the software and hardware are in place, and then HAS operation. So I'm going to skip this. So we also do a comparison between our HAS and IBM SoftLayer also has something like this. And OpenStack, ironically, is gradually trying to do something similar for HAS. And then this is the kind of comparison we have along the lines of how they isolate the network, can they do network traffic analysis, can they do load balancing, and so on. So this is my final slide. So what did I say? I say DNN is important, right? It looks like this wave of AI renaissance, right? The reason we talk about this AI is because deep neural network. Nothing else. Because deep neural network is very powerful. That's why we talk about AI. It's not out of the blue, we just talk about AI. It's because of deep neural network. And deep neural network, you need to train. That's the name of the game. You give me a large number of examples, then I can go through this DNN training process to extract the knowledge, build up useful DNN model. And that's why you need some kind of DNN training appliance or service to speed up the process of DNN training. And then in that process, either we can build a DNN appliance for more like private cloud deployment to speed up, or you can use a set of DNN training appliances together with HAS. You can build a DNN training service. Okay, so that's all I have. Thanks.
Thank you very much.福原さん will make a summary of this. OCPJ の運営員の福原さんに今のキーノートだけなんですけれどもサマリーして説明をしてもらいます。よろしくお願いします。
みんちゃん、今ですね、ドクター・チェからたくさんのメッセージを話していただいたんですけども、ごくごくあえてちょっとキーエッセンスだけにサマリーしたいと思います。最後のページに書かれているのと、あと皆さんのお手元には日本語の翻訳されたスライドも載っているので、大体細かいことはそちらを見ていただければ分かると思いますが、キーポイントだけです。ここでまだ言ってますけども、AI がいろいろ世間で騒がれていて、もうレボリューションが起きていると。そこにおいて DNN、機械学習って言ってしまっていいと思うんですが、機械学習キーですねと。それをするための、機械学習するための、サービスというものを考えたときに DNN のトレーニングアプライアンス、ハードウェアアプライアンスとハードウェアをリモート管理、自動管理できるようなハース、糸になハース、この組み合わせが最適でしょうというのが一番のメッセージだと思います。でですね、最初のパートが機械学習をするためのフレームワークのパートです。でこちらではですね、こういったアプライアンスがすでに用意されていて、 このアプライアンスの中は何かというと、CPU とともに GPU ですね、GPU を積めると。その GPU も非常に安価な安い価格で積むことができますというのがこちらのアプライアンスの特徴だと思います。でさらにこのアプライアンスの中ではソフトウェアのサポートも入っていて、こちらに書いてありますけども DNN のトレーニングフレームワークカフェその他2番目の列2番目のサポーテッド DNN トレーニングフレームワークってあると思いますが、あそこに書いてあるようなものがすでにサポートされています。でこれらのフレームワークは GPU が非常に有効だというふうに分かっているフレームワークなので、場合によってはですね機械学習何でもできるっていうとちょっと語弊があって GPU に合わないというようなアルゴリズム実際にはあるんですが、こちらでサポートしているものはそういったものではなくてちゃんと有効なものというものをサポートしています。でハースの方はですねこちら以前からイトリで取り組んでいるバンピですねベアメタルのサーバーにイーサーの MAC アドレスだけ振ってあとは物理的な決済さえすればそれ以上のハードウェアのコンフィギュレーションはリモートで全部できてしまいますよ、自動でインストールできてしまいますよというフレームワークがあります。それとともにネットワークのですね仮想化というのも含まれていて、そんなものを組み合わせていくともう完全にリモートでハードウェアレベルのサービスができるんではないかと、コロケーションしなくてもハードウェアレベルのサービスができるでしょうというようなものがあると思います。で今申し上げた2つですね DNN のトレーニングアプライアンスとこのハースのテクノロジーを組み合わせることで機械学習のサービス化というものができるんでしょうというようなことが3枚だと思っています。以上です。ご質問はありますか？どうぞ。
日本語ですいません。これはすでに
これらの仕組みは工業技術研究員さんの方ですでに開発済みで提供可能なものになっているんでしょうか？
はい。
という質問です。
It's already you can provide it already.
Q1 of 2018.
2018年の3月までです。来年の1月3月の間には全部提供可能と言っています。なのでキーの部分はもう開発済みというふうに思っていいと思います。
提供形態っていうのは例えばツールのライセンスとかを受けたりすることできますか？
ツールのごめんなさい、例えばソフトウェア部分だけ切り離してとかって意味です。
Sure. Then we can also talk about it.
いろいろなですね、方式を、考えうるのでお話ししましょうということです。
So we are not really a hardware vendor. All this hardware we are relying on our Taiwanese companies to do it. So our focus is mainly on software. So if you have any specialized hardware you want this software to be ported over, we are more than happy to do it.
何でもできるみたいですね。ちょっとコメントするとですね、彼ら台湾はハードウェアメインで今もずっとやってきてるんですけども、ハードウェアに、とても密接に近づいたソフトウェア管理っていうのは絶対あるんですね。でそこの部分はどうしてもハードウェアベンダーに近いところが、必要になってくるので、そこが一人の、一番の、いいポジションを取っているっていう魅力だと思います。
ありがとうございました。